Hi everyone, so we're going to start with reactions now. Okay, we talked a little bit about properties of ethers, how to name them, how to think about them, but for the reactivity, we need to consider two reactions of how to make ethers or preparing ethers, and then how, once we have an ether, how do they react? So first, how do we make an ether? So this is a new reaction, so please include it in your mechanism portfolio and your reaction map. This is called Williamson ether synthesis, and it takes advantage of alcohols because you're almost there, right? This is half of an ether. Then you just need another R group, which we're going to have right here. So to get this going, we need to get rid of this H first. So we do that with a strong base. And the strong base that tends to be used, rather than sodium hydroxide, we use a stronger base called sodium hydride. So what sodium hydride should be thought of as a sodium ion, Na+, and hydride ion, H-. And this is the part that we need. So that hydride ion comes in, and the most acidic part of this molecule is this H. So this hydride grabs H, and that bond breaks and puts the electrons on O. Let me draw that out a little bit more clearly here. Hydride from sodium hydride comes in and takes this H, just deprotonates it, this simple acid-base reaction, except instead of NaOH, we use a stronger base, NaH. Now we get this strong alkoxide ion, which is now our base in solution, and we're going to react it with an alkyl halide. And this alkyl halide is going to provide us with the R group that we want to get our ether. So in essence, this is an SN2 kind of reaction, backside attack, and this leaves all at the same time. So there's our asymmetrical ether, and then we have halide ion and sodium counter ion left over from NaH. And what happened to the hydride? It became H2, which is pretty flammable. You can make some pretty nice flames with that stuff, but it's also gaseous, so you can just evolve the gas. All right, so our main molecule of interest, though, is making that ether. So please remember this as the Williamson ether synthesis. This is how we make an ether. Now let's think about this question. The top method is fine for making, again, MTBE, methyl tertiary butyl ether, or butyl methyl ether. And then the bottom method, though, is not so great. So would you take a moment and work through the top, verify that it works using the Williamson ether mechanism that we just went through, and then think about doing the same thing, but with the bottom set of reagents, and see if you can think of any reason why the bottom one would not work as well. Okay, everyone, the key to this is remembering some of the concepts from first quarter. The first step is not a problem. It's just acid-base reaction. You just grab a hydrogen with a strong base and you make this alkoxide, tert-butoxide in this case. You attack the methyl iodide and release the iodide. Not a problem. And that's because this is an SN2-like reaction. You're attacking a primary group right here. It's only attached to, actually it's not primary, it's methyl, right? So even less steric hindrance. It's a methyl halide. So virtually very little steric hindrance, only from hydrogens. In this case, you just deprotonate. The first step is not a problem. It's the second step that's a problem. I think you guys see that there's all this bulk here, so the electron density of this tert-butyl group is going to repel the methoxide from coming in. So if this is SN2 and we're trying to do SN2 on this tert-butyl iodide, this is going to be a tertiary alkyl halide. That's not so great here for attack. It's going to be very slow. So that's why I need to keep in mind Williamson ether synthesis works great because it's like an SN2 reaction. It's going to be best for methyl or primary alkyl halides. Secondary, okay, but it's better to stick with primary or methyl, and definitely not tertiary. So tertiary, you would go another route if possible. Let's practice with this a little before we talk about that. Show reagents you would use. Think about the Williamson ether synthesis. So that means you are making this ether, what are you going to start with here? What are you going to use as reagents to make this ether? Because Williamson ether synthesis means you're synthesizing an ether, you're making an ether. So for this one, I would think about either way, is it this alkoxide that attacks here, which is primary, or is it this alkoxide that attacks here, which is secondary? What do you guys think is better? Well, with SN2, it's definitely faster to attack a primary, less steric hindrance. So that sort of tells me what my cleavage point is. I want this alkoxide. So that means I'm going to start with cyclohexanol. I'm going to deprotonate it with sodium hydride. I'm going to make the alkoxide. And then I need some kind of a leaving group on here where the O is. I need something for this to attack and leave. So this is going to attack backside, and I get this. So that's a possible synthesis. All right, so you always want to think about that. Which way is better to attack? Is it better for this group to attack this group, or better for this group to attack this group? Okay, the alternative that would not be as good is if you said this alcohol would attack. First you would deprotonate it, then you would have the cyclohexanol as an alkyl halide. Okay, then it would not be as good because this is secondary. So I'm going to put that this would be slower in getting to the same product. Okay, so on your own you can try part B as well. Consider the same thing and check your answer, 13.5 practice problem. Now, another way to make an ether would be to use an alkene as a starting material instead of an alcohol. And in this case, you can make tertiary, secondary, primary, methyl. You can make whatever alcohol you have turn into an ether just by changing the solvent here. So let's review. So you've got a double bond here. The only thing is this is Markovnikov. So you're only going to get the OH on the more substituted carbon, which is this one. And because we use water, we get an OH group added here and an H group. That's water, HOH. That's water. If we change this solvent to an alcohol, you'll be able to get an RO group, but again, this is Markovnikov. So just keep that in mind. And look, in this case, it happens to be tertiary. You could also have a secondary or primary, just as long as it's Markovnikov and more or equally substituted than the other carbon, will you get that group adding there. And then if you recall, the mercury is still attached here, and then that gets switched with hydrogen in the second step, the reduction using sodium borohydride. So now let's think about this. Here's our alkene. We're going to apply this reaction by saying, okay, this is Markovnikov addition, so that means I'm going to add the group to here, and the group I'm adding is this. Normally, when we use oxymercuration, we use it with water, we get an OH group. But instead of OH group, we're going to get an OET group. So in order to do that, I use mercuric acetate. And then as a solvent, I use the alcohol that I need. In this case, I need ethanol, so ETOH. And then you follow it with NaBH4 to get the mercury off of the position here. So there's going to be an HGOAC after the first step. And then you're going to replace it with hydride in the second step. So after the two steps, you're going to end up with this molecule. And that's because the point of this exercise was you just control the solvent there. The use of the solvent, especially protic solvents, really get involved in the reactions. This is a protic solvent. It got involved in the reaction. So you got to be careful with protic solvents in that way. So let's recap, okay? So for this session, we talked about making an ether, but you want to make sure that you are considering that the second step is an SN2. So it's best to have the alkoxide attack a primary or methyl group, alkyl halide, instead of a tertiary one. So as long as you can do that, you are going to have a pretty good Williamson ether synthesis. You definitely don't want to do this on a tertiary. Okay, so that's a no-no. If you do want a tertiary ether, then you might want to think about starting with an alkene, having two R groups, and then here you have a tertiary, or three R groups, you have a tertiary alcohol if you use oxymercuration in water. But if you want an ether, which is the point of this chapter, you can use alcohol as your solvent, and you'll get a nice tertiary ether that way, if that's what you want. But again, it doesn't have to be tertiary in this case, it just has to be Markovnikov addition. Now let's talk about once you have an ether, what do you do with it? So these are new reactions as well. So let's try an ether cleavage reaction. We've talked about oxidative cleavage before. This is cleavage of an ether. Cleavage just means cutting a molecule. So you're gonna end up with smaller pieces. So in order to break an ether apart, you can do the opposite of what we did over here, which is to use a base to add groups onto the alcohol. We're going to use acid, the opposite of base, to cut it. Let's see if you guys can figure this out, okay? And I'll give you a hint. The ether has this oxygen, which is the most reactive part of an ether usually, is the oxygen with its lone pairs. And I'd like you to think about how those lone pairs would interact with HX. So some kind of HCl, HBr, HI. How would that break the molecule into these pieces? See if you can think up a mechanism for this, and then we'll go over it. All right, so the basic understanding with this one starts with the basic site of the ether, and we've got an acid here, HX, so this is the partial positive, the partial negative. So we're going to attack there and protonate this ether. That's going to kick off this reaction here. And let's stick with the color coding here. This R group will be red, and the other one will be blue. Once we protonate this ether, then we want to think about how to get this halide ion back onto the molecule. Now remember, with this protonated, this is a good leaving group if you attack here, or if you attack the other R group, then this is a good leaving group as well. So it's either way, you get a good leaving group because of the protonation step. So first, let's arbitrarily pick this one as opposed to this one, but you can see they're both alkyl halides and they both happen. So if by chance this one comes over here, maybe it's less sterically hindered, for example, then it'll come over here and we'll just do an SN2 reaction. Backside attack, release a good leaving group. So basically it's just SN2 reactions, which you already know about. That will give us an alkyl halide. This guy, see, that's how we got that. And then we'll have this leaving group here, the ROH group. This is an alcohol. Okay, so this is called ether cleavage because we're choosing to break one of these bonds. If I do this mechanism here, if I choose this alkyl halide to attack, then I'm basically breaking it off here. So I'm cleaving through the ether either on this side, or I could have shown how to make this alkyl halide. If X attacked here, then I'm cleaving this bond here. So one of the two bonds cleaves, you're left with then an alcohol for the other half. Now this alcohol is not one of the products, so let's see what's going on here. Once we make this alcohol, and again, it doesn't matter if it's this alcohol or this alcohol, just depends on what attack is favored, if there is one, otherwise you get both. We need to try to make an alkyl halide out of this, so you might think, well, I'll just take the halide from the HX and I will attack the R again. But remember, this is not a good leaving group here. So you'll need another equivalent of HX to kick off another reaction like the one we just did. So hydroxyl groups can also get protonated. Of course, we've done this a million times now. And we've, well, maybe not a million. So we have X minus, and we're going to attack SN2. Again, this is a good leaving group right here. So I'm going to release that. And then that will explain how I get this alkyl halide RX as well. So I've turned both of these groups now into alkyl halides. This oxygen, what happens to it? It is this water molecule here that leaves. So that's how we get H2O, which is right here. And here it is with the correct coloring system. So R groups turn into alkyl halides, and then you have water, which is the product of having this oxygen take off as water. So this is called ether cleavage because you're taking an ether and sort of breaking it into pieces. So let's do a practice problem using the ether cleavage together. So in this case, we have a symmetrical ether. And so you can picture that the HBr is going to help get this oxygen protonated. That will result in protonation here. And then now these R groups, this is a good leaving group now for either this group or a good leaving group for this group. And it's because it's symmetrical, that's the same. So let's say, sorry, this is a plus sign here. So let's say bromide, which is the byproduct of HBr dissociation, okay, can come in and dissociate this leaving group as an alcohol. And then this alcohol can combine with the alcohol if bromide comes in this way, and then we're going to get water. So let's show the product. So when this attacks here, this is going to give us Br here, and it will give us that on the other side as well. Okay, so let's try these now, and then we'll come back and check our answers. Alright guys, so we're back, and looking at part B, it is not so straightforward, so that's why it's good to go through more examples, because you don't always get just whatever they tell you here. You know, it's always a few extra things to consider. So let's look at that. So here, when iodide attacks after this gets protonated by HI, you'll get this, but this is weird. This is an alcohol, and we said we didn't get an alcohol product per se. We got multiple alcohols that then dehydrated. So let's think about this. We should have two alkyl halides. So when we have the same molecule as the intramolecular, cyclic molecule, if I attack here, then this opens up to an alcohol, but the alcohols get protonated by acid. So this is going to pick up another H, and then we're going to have the iodide come in here and let go of that. So this is an SN2, another SN2 reaction here. So you have both SN2 reactions, but on the same molecule, cyclic molecule. So that means our final product will actually be this diiodide with, make sure you have 4 carbons that don't get lost there. So your final products are 1,4-diiodobutane. And the way that you would know that is to follow through the mechanism. That's why it's useful to have the mechanisms around. Now, part C is good to go through because we see that you don't just automatically get the 2 alkyl halides in all cases. This is a situation where you really have to know the mechanism. So after the O gets protonated, then the bromide has a choice of attack of either here or here. And why don't you guys think about that? Are both equally likely, or is one better than the other? And which one and why? Well, if you recall, this is an sp2 center, and it's not great for attack by a nucleophile, and that's because sp2, there's several reasons for that. First, it doesn't make a very positive, partial positive charge there because it's sp2, which is closer to the nucleus, more S characters closer to the nucleus, and it doesn't like to stabilize positive next to the nucleus because the nucleus is positive. Another reason is because these pi electrons here create electron repulsion for a nucleophile to come in and attack. So we will prefer to stay away from that. Therefore, the best product we can get here is going to be the phenol. So this is going to be released into a phenol, which will not react further because this is not a good place for a leaving group. So that's why aryl halides do not react very well with SN2. So if we react here, though, we can get 2-carbon bromide, which is ethyl bromide. So these are your products for part C. So you do have to consider hybridization and the fact that this second step, these are SN2 reactions. Just like with Williamson ether synthesis, cleavage is also SN2. So I recommend for practice, write out your ether cleavage and go through more problems in 13.10. I think there are several more you can do, and just to get more practice, and include that in your reaction map as well.